Okay, so section 8.2, we are working with series. A series is when you add up an infinite number of terms of a sequence. And we want to see if the series converges or diverges. If the series converges, it means it's going to have a finite sum. So you've worked so far with geometric series. You learn that the harmonic series, geometric series converges if the absolute value of the common ratio is less than 1. A harmonic series will diverge, and we learn that even though if you have a series where the terms are approaching 0, that's not adequate to say that the series converges, and the harmonic series was an example of that. And I want you to take a look at this series. So let me give you a moment to copy this section 8.2 example down. Okay, so what's this series here? I call this series, well, this series is called a power series. What makes this series different than like if you had a series like this? Let's say the series were, starting at n equals 1, going to infinity, so it's an infinite series. Let's say it were something like 1 over 3 to the nth power. Okay, so what's the difference between this series here and this series? Okay, good, Colum, good, Tina. There's an x, there's a variable x in my series. So when that happens, we call the series a power series. Okay, we call the series a power series. And power series can converge or diverge just like a regular series. All right, and really what we want to know is for what values of x does this series converge? I mean, really what we're interested in is where the series converges. So what does this series remind you of? I mean, what kind of series does it resemble? Does it resemble a harmonic series? Does it resemble a telescoping series? Does it resemble a geometric series? What kind of series does this power series most closely resemble? That's right, Michael. It definitely resembles a geometric series. And if we write this series in the right form, we'll see that very nicely. So let's go and take a look at the solution here. Okay. So what I do to give you an intuitive feel for the series is I write out here the first 4 terms of the series. All right. Are there any questions on this part here? Okay, so the power series is a geometric series, but always with the geometric series, we need to think about what the common ratio is. Well, the common ratio here is x over 3. Now, of course, if I take, how can I sort of see that? Well, there are really two ways. I could take like x squared over 9 and divide that by x over 3, and I'll get x over 3. And I can take x cubed over 27, maybe I'll put that in blue. I can take x cubed over 27 and divide that fraction by x squared over 9, and I'll get x over 3. And so forth and so forth. It's a common ratio, right? A common ratio. But sometimes it's easier to do it this way. If I take the first term, x3, what must I multiply, x divided by 3 by to get x squared over 9, which is the second term? X over 3 times what equals x squared over 9? Yeah, that's right, Rodrigo, x over 3. Okay, and then I don't think it's too hard to see. Hold on, let me get that 3 a little nicer here. And hold on. The 3's are always the toughest to write for some reason. There we go. Now, if I take x squared over 9, and multiply that also by x over 3, we're going to get what? We're going to get what fraction? Good. Good, Tina. X cubed over 27. So, it's clear that, we're picking off the terms here. I mean, sometimes I find that an easier way to determine the common ratio, right? But now that we have it, I mean, how many of you kind of like that way for figuring out the common ratio? Okay, Tina likes it a little bit better. Well, people differ, and that's fine. But what we want to do is, for this power series now, we want to find the values of x for which the series converges. And of course, for a geometric series, what do? I take the common ratio, the absolute value of it, and set it less. Well, I want to say this the right way. A geometric series converges when the absolute value of its common ratio is less than 1. Okay, so this geometric series you've seen before, what you figured out is you figure out the common ratio and take the absolute value. Is it less than 1 or not? If it's less than 1, the series converges. If it's greater than 1, the series diverges. For geometric series. Here, though, we're looking for values of x for which the series converges. Well, that means since the power series is a geometric series, we're going to take its common ratio, which is x over 3, take the absolute value of that common ratio and set it less than 1. And then I'm going to solve for x. So of course, if the absolute value of x over 3 is less than 1, then x over 3 is less than 1 and greater than negative 1. Okay, and then if I multiply through that inequality by 3, I'll get x is less than 3 and greater than negative 3. Okay, I mean, just multiply through by 3 everywhere here. Yes, not no. Yeah, I have a good question.
Did you say if the common ratio is less than 1, then it diverges, and then if it's greater than 1, it...
If the absolute value of the common ratio is less than 1, then the geometric series converges. If the absolute value of the common ratio is greater than 1, then the geometric series diverges.
Okay.
Okay, all right. Well, okay, so, all right. So the interval of convergence then is going to be, well, the interval of convergence, we call it an interval of convergence here. Let me see, a good question here. Why did you take the absolute value sign off? Okay, all right, Tina, one moment. Let me do an analogy here. One moment. I mean, let's just take something simple here. Let's say that you have the absolute value of A is less than 1. Well, then what's that tell you about A? What values of A would satisfy this inequality? A could be greater than -1 and A could be less than 1. So this inequality is equivalent for the second inequality, and that's all I did over here. I just, I mean, that's how you work with a compound with absolute value. That's how absolute values work. But I mean, yeah, okay, no problem, no problem. Well, all right. So the interval of convergence, and that's defined as the x values for which the series converges. The interval of convergence is x is between -3 and 3. And so now we can get the sum. We can get the sum. So again, for a convergent geometric series, the formula is A divided by 1 minus R. We established that the common ratio was x over 3. And the first term of the series, you know, A stands for your first term. First term. And, you know, I wrote out the series up here, and here's the first term, x over 3. There it is. So, yeah. And so the sum is x over 3 divided by 1 minus x over 3. And WebAssign would accept that answer, but you could certainly multiply the numerator and denominator by 3 just to clear out the fractions. And then the sum of the power series is going to equal x over 3 minus x, so long as x is between -3 and 3. If x is any value outside that, it's not going to work. But the beautiful thing is we have a formula now. We have a formula for this power series. We have a formula. All right, are there any questions on that? All right, I'm going to ask a quick question here. So if I had the sum where I goes from 1 to n of 2 to the nth power over 3 to the nth power. If I had that, could I use this formula to find the sum of that series? I mean, could I use that formula there? Michael says yes. And why is that, Michael? Why could we use this formula here? That's exactly right. X can be between any value between -3 and 3. And so if we applied the formula, we would have 2 divided by 3 2 divided by 3 minus 2, and that's just going to equal 2 over 1. Okay? Okay. By the way, could we use the formula for this series here? That's a 3, right? Could we use the formula for this series here, the series where n equals 1 to infinity of 5 over 5 to the nth power divided by 3 to the nth power? Could we use our nifty formula here to find that sum? Tina says no, and why no, Tina? That's right. 5 is greater than 3. 5 is outside my interval of convergence. X equals 5. You know, this is so like here I had let X equals 2, right? Or the first little example. Here now I'm letting X equal 5 for this, this little example here. And 5 is not in the interval from -3 to 3. Let me ask you, should you spend effort? Should you spend effort trying to find this sum of this series? No. What's happening to the terms of that series? I mean, the terms of the series, of course, could be expressed as 5 over 3 to the nth power. And that's right, Cologne. And that's right, Tina. The terms are getting bigger. The terms of the series are getting bigger with n. The terms are going to grow in the series. There's no way that series converges. So, it won't even make sense to try to find the sum of that series. So this is a little preview of what you're going to see in section 8.5. In 8.5, you're going to be dealing with a wider variety of power series, but at least you've seen one. Are there any questions on that? Okay, all right. Well, what I'll do now is let me stop the recording.